Is it required?
Yes, sir.
Okay. Is it visible right now?
Yes, sir.
Okay.
After the presentation starts, you please keep it in slideshow mode, sir, and please switch on your video while presenting.
Okay, sure. Is presentation visible right now? Can you see
Yes,
it?
sir, I can see the PPT.
Okay, let me open my camera also. Is it visible?
Yes, sir.
Okay, nice. Okay, let me start right now. One
Yes, sir,
sec.
I will introduce you to the party.
Okay.
Please
Then
wait
I
a
can
minute,
start.
sir. Good afternoon, everyone. I welcome all the participants to our session, today's session. And today's session is going to be handled by Dr. Korhan Senses from Turkey. And I take the privilege in introducing our today's resource person. Dr. Korhan Senses is working as assistant professor in Trakya University of Turkey, and he did his bachelor's degree in electronics and communication engineering, and also he has a bachelor's degree in business administration, and he did his master's degree in the year 2011 from Namik Kemal University, and he obtained his doctoral degree from Kadir Has University in the year 2016. His fields of interest include 4G, LTE, 5G, network function virtualization, software defined networking, indoor positioning systems, and spatial modulation. He has served various academic titles like research assistant, lecturer doctor, and assistant professor in various educational institutions in Turkey. And also he is handling various academic and administrative positions like co-head of the department and various coordinator positions also. To his credit, he has a number of SCI and other prestigious journals, and he has also published papers in several international conferences. He also has IEEE membership and acting as editor for various reputed journals. To his credit, he has Best Paper Award awarded twice, and also TÜBİTAK Priority Areas PhD Scholarship for the year November 2014. Sir, thank you for accepting our invitation and being a part of our workshop. If I have pronounced anything wrong, please excuse me, sir.
No issues.
For you, sir. Thank you.
No issues. Thank you again for your kind invitation. Okay, if we are ready, let us start, right?
Yes, sir.
Okay. Today we will talk about novel routing protocols for wireless sensor networks. Actually, in our studies, especially in my PhD, we have designed two routing protocols for wireless sensor networks. One of them is LEFCA, Low Energy Fixed Clustering Algorithm, and other one is Maltop LEFCA. Also, it is an extension to LEFCA protocol, but it has some additional novelties. So I will try to explain you these two novel routing protocols, and also I will try to show you some international aspects about the wireless sensor networks and also some future topics today. So let me, okay, it's okay right now. Let us start as a motivation. Now, we know that wireless sensor networks are widely used in different areas, especially nowadays, disaster relief, target tracking, environmental control, smart cities, medicine, and also highly used in healthcare applications. And to distribute the sense data, different approaches are used in the literature. These are direct transmission, multi-hop routing, and clustering. In direct transmission, sensor nodes directly communicate with base stations, and in multi-hop routing, some sensor nodes are used as especially relay nodes, or in other words, gateway nodes, to provide communication with especially base stations, remote base stations. And finally, in clustering, there is a cluster head which is responsible to collect information from the sensor members and then transmit this information to the remote base station. So our proposed LEFCA protocol is a clustering protocol, and our proposed multi-hop LEFCA protocol is a combination of clustering and multi-hop routing. So as a motivation, we know cluster topologies in wireless sensor networks change very frequently, and there are some problems. Which are them? Increase in energy consumption, for example, decrease in network lifetime, additional network overhead. So our proposed LEFCA tries to solve these problems by using fixed clustering or changing the cluster head election process of the existing protocols. So as a related work, here Leech is the most known routing protocol in the literature, and Leech protocol has two phases, setup phase and the steady state phase. In the setup phase, Leech tries to form the clusters, and in the steady state phase, it aims to transmit the information to the remote base station. And in Leech protocol, there is a probabilistic cluster head selection and formation process. So therefore, due to this probabilistic idea, sometimes in Leech, there is no cluster formation. So therefore, sometimes, for example, for some rounds, you cannot measure anything. You cannot get any information measurement from the environment, and you cannot transmit anything to the remote base station. So this is a very important problem, especially it is when you use wireless sensor network in, for example, healthcare applications, for example, in fire measurements. So this can be very important problem for us. So therefore, proposed our LEFCA protocol also noticed this problem, and we tried to solve this problem in our LEFCA protocol. I will explain in details in the following slides. So there are extensions to Leech protocol, and they are trying to increase the especially energy efficiency, increase the lifetime performance of traditional Leech protocols. So when you look at the literature, you can find thousands of protocols that are trying to increase the performance of Leech protocol. So for example, LeechF is another related work. For example, Mode Leech protocol. DEEC is another related work. Stable election protocol, also most known, and another related work about the literature. And also there are so many extensions. Okay, let me tell and explain LEFCA to you in details. Our LEFCA protocol aims to use fixed clustering and cluster head determination via base station approaches together, and it uses intelligent cluster head determination mechanism, which tries to especially elect the nodes that are almost at the center of their associated clusters at the beginning of the algorithm. And also, LEFCA uses a threshold-based cluster head change mechanism, and it aims to exploit the energies of the cluster heads before electing a new cluster head. And we know that this idea, this exploiting this abusement, is not proposed any of the existing algorithms. So the novel part of Lefka comes from this idea. But this is also a dangerous idea because when you exploit the energy of a cluster head, you can lose whole information, whole communication related about the network. So therefore, here also, you need to define the proper threshold value. And also we did it according to mathematical derivations. I will also explain it in details. Because you need to provide full network connectivity because Lefka is proposed especially for critical applications, as I said before, especially for healthcare applications, fire measurements. So therefore, we need to be careful while designing the threshold value of Lefka. So I will explain also in details. Our Lefka also has two phases, setup phase and the steady state phase. But our protocol is a fixed clustering protocol. So in the setup phase, we define the cluster formations partitions only once at the beginning, and then we decide the most suitable intelligent cluster heads at the beginning. So after that, our setup phase is completed, and then in steady state phase, we just try to transmit information, transmit measurement from environment to the remote base station by using the cluster heads. So in our cluster formation stage, there are two main messages in the network, in the wireless propagation channel. Cluster head advertisement message and cluster members join request message. In cluster head advertisement message, when a cluster head is selected as a cluster head, it broadcasts a wireless message to the network and says that I'm cluster head. So when the member nodes got this message and then they said they try to join to the associated cluster heads, and they are trying to join which are nearest, closest to them. So by using these messages at the beginning, our cluster formation completed. So for several rounds, for example, for 100 rounds, maybe 500 rounds, our cluster heads stay constant. They are not changed. So therefore, there is no need to make these messages again and again in each round. But in leech-based protocols, as we said before, it uses probabilistic function to select cluster heads, and in each round, at the beginning of each round, in each network, cluster formations is changing, cluster heads are changing. So therefore, you need to exchange these messages for each round in leech network. So our Lefka network here provides to decrease the number of messages that are transmitted in the network. So also it decreases the network traffic. In addition, here by decreasing these messages also, you can save, as expected, additional energies. So when our cluster formation completed, our cluster head is responsible to transmit TDMA schedule to the network. For example, in a cluster, we have 10 members and one cluster head. So we need, as expected, 11 time slots, 10 time slots for members and 1 time slot for cluster head. So our cluster head collect the measurements in each time slot. Each member transmits the measurement, and then our cluster head in his associated time slot transmit information to the base station. So the main important part of LEFCA is cluster head change decision part, because we use threshold-based cluster head change decision, threshold-based cluster head changing. So therefore, also we said we aim to exploit the energies of the cluster head before electing new one. So to provide this, we need to use actually lower threshold value as expected. So here we use lower threshold value, and this lowest threshold value provide us to especially exploit the energies of the cluster heads, but by making minimum the number of message exchanges and also number of packets that were used just only for communications between cluster members and member nodes, and also with normal sensor nodes. Therefore, we got additional energy savings by using this exploiting. So to provide full network connectivity, we said before, we need to be careful because we aim to use LEFCA especially for critical applications. So therefore, we need to have proper suitable threshold value. So, but also we want to exploit the energy. So how can we decide this? We can we can find this proper threshold value by using this equation. This equation shows us the energy dissipation of a cluster head while transmitting message to the remote base station. And here, this term shows us the distance between cluster head and base station. And here, as you see, there is fourth power. So the fourth power is coming from the crossover distance. The crossover distance is an important important thing in wireless communication environment. And for our specific values, deterministic bitrate and other parameters, this value is 87 meters. In our network, if the distance of a cluster head or any sensor node is higher than 87 meters while sending information to the base station, it will consume its energy according to the fourth power of that distance. If it is lower than this distance, it becomes second power here. So therefore, we decided to use especially this equation, and we considered the worst case for us to determine the proper suitable threshold value for us. So here, what is the worst case for us? For example, we have an outside base station and we have 100 sensor nodes that were distributed environment randomly. So we considered that we have only one cluster head and the other all nodes are normal nodes, and our this remotest cluster head that is located in the origin and the other all nodes are sensor nodes. There is only one cluster. So how much energy will this worst case cluster head consume for a one route? We tried to calculate this value, and according to our calculations, we have found that according to our specific parameters, it is 0.005 joules. And here, our sensor nodes start with 2 joules initial energy at the beginning, and there are 100 sensor nodes, as you know. So here, and also, you know, we want to exploit the energies of the cluster heads, but also we have to provide full network connectivity, assurance in network connectivity. So therefore, we decided to use the threshold value 10 times higher than this value. So we decided that the energy of a cluster head is 0.05 joules in Lefka network. So let me summarize you Maltop Lefka in one slide because it has main ideas with Lefka protocol. It's an extension to Lefka protocol. Now, our Lefka protocol, as you see, is a fixed clustering protocol. Also, Maltop Lefka is a fixed clustering protocol, and it has same idea, same things in Lefka protocol. But you know, for example, let you consider that we use Lefka protocol here. In Lefka protocol, we know that, for example, these cluster heads are responsible to collect information from the members and then transmit this information to the remote base station. For example, for cluster 1, node 5 will transmit directly information to the base station. For example, in cluster 4 also 20 will do like that. In cluster 3 also 15 will do like that. But in Maltop Lefka, node 5 will transmit information. Instead of transmitting it to the base station directly, it will transmit it to the nearest neighbor cluster head. For example, for here, it is 11. And for example, for 15, the nearest forward direction neighbor cluster head is node 20. So it will transmit the information related about cluster 3 to the node 20. And finally, node 11 also is responsible to transmit information to the node 20. And finally here, node 20 is responsible to transmit whole information related about network to the base station. So also in Maltop Lefka, we can have some problems. It is as expected. We can expect that. So here, to solve these problems, what can we do? For example, the main problem, if any connection problem occurs in node 20 or cluster 4, what will happen? Because let you think we are using this Maltop Lefka in, for example, fire measurement. So then what will we do? This is an important problem for us. So therefore here we need to be careful while determining the cluster heads. So for this problem, what can we do? This is also an open research problem for us in Maltop Lefka network. So let us show you, let me show you the simulation results. Here, this result shows us the impact of number of clusters. As you remember, we said that at the beginning, Lefka protocol uses intelligent cluster head selection. So therefore, here, when we use intelligent cluster head selection at the beginning of Lefka network, our LEFCA network provides additional energy savings when it is compared with random selection. So therefore, we decided to use intelligent cluster head selection at the beginning of LEFCA network. And also this figure shows us the impact of threshold value in network lifetime. As you know, we use lower threshold value to exploit the energies of the cluster head, but also it is possible to use different threshold values in LEFCA network. And this figure shows the energy map of the network. For example, as you see in Leech network, almost all nodes are black. So this means that you cannot get any measurements because these nodes are dead. In other words, out of battery. They cannot measure, they cannot communicate. So therefore, from almost all parts of the network, you cannot get any information. But in LEFCA network, it is still possible to collect information from all parts of the network, as you see from the figure. So therefore, LEFCA is suitable candidate, especially for critical applications, especially, as we said before, fire measurement, especially healthcare applications. And this figure shows the remaining energy of LEFCA network. And as you see, LEFCA provides robust and best energy performance when it is compared with other protocols. And this figure shows the number of alive nodes. And actually here it has also robust nature, and it has almost a linear nature, and it has the best performance again when it is compared with other protocols. And this table shows the network lifetime results of LEFCA and other protocols. And we obtained this table by using independent iterations. In each iteration, the network generated randomly, and for the same network, we used each algorithm in same topology, and we obtained the lifetime results in terms of rounds. And according to 100 iterations, we got the average lifetime results. And according to our results, it is seen that LEFCA has again the best performance when it is compared with most known protocols in wireless sensor networks. And this figure shows the total data transmitted to the base station. In other words, we can say total number of packets transmitted to the base station. So again, as you see, LEFCA has the best performance. And for different node densities also, we got results. What will happen when we decrease the number of nodes in the network, and what will happen when we increase the number of nodes in the network, and what will happen when we put base station inside of the sensor network. As expected, the lifetime of LEFCA and other protocols increased because the transmission distances decreased. So this figure shows the comparisons of LEFCA with multi-op LEFCA. Briefly, we can say that multi-op LEFCA provides 10% approximately additional energy savings when it is compared with LEFCA protocol. So, as a conclusion, today I tried to explain you two novel protocols for wireless sensor networks. One of them is LEFCA and other one is multi-op LEFCA. LEFCA protocol is a fixed clustering protocol. It has threshold-based cluster election strategy, and it tries to exploit the energies of the cluster heads to provide additional energy savings. when it is compared with other protocols, and Lefka is a good candidate, especially for critical applications such as disaster relief, such as environmental monitoring, especially fire measurements, and also healthcare applications. Maltop Lefka is an extension to Lefka protocol, and it tries to combine Maltop routing with clustering ideas, and it is also important, and it is also a good candidate again for critical applications. For Lefka and Maltop Lefka as a future study, the first one is the problem of Maltop Lefka, the nearest cluster to the base station. It has a lot of load, as you see in the figure. Also, maybe as a future study, can we apply artificial intelligence based ideas, machine learning, deep learning based ideas to the Lefka protocol at the beginning, especially at the first clustering stage? Is it possible? Also, can we apply Lefka to large-scale networks? Is it possible? This is also another open research problem for us. So with researchers, we are open for collaborations, actually. And let us get questions, if any. Any questions?
Sir, questions are posted on chat box for your reference.
Okay. Any questions?
Sir, there are some questions, sir. Let me read. What are the tools or simulators used to implement the protocols?
Any questions?
Sir, can you hear me, sir?
Yeah, I hear you right now.
Sir, the question is, what are the tools or simulators used to implement the protocol?
Okay, it's a good question. We used MATLAB. We designed our Lefka and Maltov Lefka protocols in MATLAB, but also they can study with Network Simulator 2, 3, NS2, NS3, and also it can be done via Python. It is possible, but we worked with MATLAB. Any more question? Okay, I think there is no more question, right? Also, you can type via chat box. They can type, no issues.
Sir. Participants, please post in the YouTube chat box, YouTube comments. Sir, one more question is there.
Yes.
In MATLAB, which toolbox we have to use?
Actually, we didn't use any toolbox. We just designed the code by using some specific functions which were generated by us. But yes, you know, MATLAB has good toolboxes, especially for nowadays machine learning and deep learning. So also by using these toolboxes, they can enhance the performance of Lefka. As I said before, at the beginning, especially the clustering stage, they can make some good improvements by using artificial intelligence toolboxes of MATLAB. I think it is possible. So we are open to collaboration with these ideas, especially with Master of Science students, PhD students. So therefore, it is possible to study with them. Any more questions?
Okay, thank you very much, sir.
You are always welcome. Thank you for your kind invitation.
Accepting our invitation and sparing your valuable time with all of us.
It was pleasure for me. Always welcome. And for the future events, inshallah, we can meet again. There is no issues. And I am open for collaborations with your researchers, especially fresh researchers, PhD students. So please provide them to communicate with me for further research opportunities together. Okay?
Sure, sir. So participants can use this opportunity given by our resource person. If they have, they want any help from our resource person, they can contact him. Now our our workshop coordinator, Dr. Aziz, wants to share his views.
Okay, thank you. It is Dr. Aziz, your microphone is closed. Can you open it?
Sir, good evening, sir. I hope you remembered me. Already we have submitted one paper in computer and electrical engineering journal. Yes.
Oh yeah. I remember, of course. How are you?
Yeah, fine, sir. How are you?
I'm also fine. Thank you so much for your kind invitation. It was a pleasure for me, and I will always come for your future events. You know, we have especially I have good relationship with your country, and I have so many collaborations with your country, with your friends. So therefore, it's always a pleasure me to join to your events. And also I have been to India 5 years ago. So therefore, always I am ready to collaborate with you and join your events.
Okay, sir. Actually, during the time of computer and electrical journal submission, we have done some work in the collaborative manner. In the future also, we would like to combinedly do our work. Then only our relationship will be continued for a long time. And moreover, I would like to thank on behalf of GMRIT management for accepting our invitation immediately and becoming the part of this FDP event, sir. I would like to thank once again from my heart. And in near future also, whenever we will conduct these kind of FDPs, we will request you to take effective sessions like what you have taken today. Your session was awesome and it was highly informative. We have received a lot of positive feedbacks for your session in the YouTube streaming and all. Again, we are all doing some research in the area of wireless communication networks. So in future also we will collaboratively work more research in the area of wireless communication. Not only especially in wireless communication, wherever the emerging trends will come, so we will focus on that, sir. I am expecting your support in that aspect.
Always I am ready to support you and your friends, your colleagues. So therefore, you know, for events, you can directly communicate with me. I will be. It will be pleasure to me to join your events and future, especially conferences and other things. Thanks again for your kind invitation and keep in touch. See you soon again.
Yes, sir. Definitely, sir. Thank you, sir.
You are always welcome. Okay, then I think I can leave, right now.
Yes, sir. You can please.
Okay. See you later.
Okay, sir.
Have a
See you.
nice evening. Okay. Bye.
Sir, please make a note. Tomorrow session will be at 9:45 a.m. instead of 9 a.m. Tomorrow session will be at 9:45 a.m. Thank you.